Hello. Welcome. I'm Norman Wildberger, and we are in Lecture 10 of this course in History of Mathematics. Today we're going to talk about infinite series. And the main mathematicians in this section is, well, first of all, Newton and Gregory, whom we've already met, but some new people, some 18th century mathematicians. Well, first of all, the Bernoulli family. Okay, so this is the most significant family of mathematicians in the history of mathematics, the Bernoullis. Jacob, 1654 to 1705. Then there was John, 1667 to 1733. Nicholas, 1687 to 1755, maybe, I'm not sure. Daniel, 1700 and 1782. So I guess two of these were brothers, one was a nephew, maybe three of them were brothers, something like this. And then we meet the giant of sort of the modern age, Leonard Euler, whose dates are 1707 to 1783. And we might mention also Joseph Lagrange, who was in some sense the heir to Euler, 1736 to 1813. And there were other figures as well. Okay, so we talked a little bit about infinite series last week when we were talking about calculus. So let me remind you what the basic setup is there. We're thinking about expressions like 1 over 1 minus x, which is 1 plus x squared plus x cubed, and so on. This is, in fact, the most fundamental of all infinite series, since it's really a geometric series. And we saw that it was a favorite of Newton, and it can be used to derive a lot of other different series. Now these days, we think about series, we study them in first year calculus, and we think about series like this in terms of whether they converge or diverge for a particular value of x. This is not really the way the 18th century mathematicians or the 17th century mathematicians thought about infinite series. They rather thought about them as some kind of extended or infinite polynomial. So these are really infinite polynomials, and one really wants to do polynomial arithmetic with them. So, for example, to justify this expression here, they would have said, well, we can justify it by cross-multiplying 1 equals 1 minus x times 1 plus x squared plus x cubed, and so on. And if we just think of that as a product of polynomials, albeit infinite polynomials, then we can expand in the usual way and collect terms. So 1 times this whole series would be 1 plus x squared plus x cubed, and so on. And then minus x times that same series would be minus x plus x squared plus x cubed plus, and so on. And then if you look at the sort of the difference between these two infinite expressions, it's kind of obvious that everything past this first one gets canceled in the second series. And so, indeed, the product of this times this is in fact 1. And that's an algebraic calculation. It doesn't really have anything to do with convergence at all. So the notion of convergence of a sequence was floating around. They were still interested in things converging, but it really didn't come into focus till probably the 19th century when Cauchy made more clear what exactly it meant for a sequence to converge. But during the 18th century, a kind of algebraic point of view was the dominant one. Okay, so we can manipulate this in a lot of ways. One very simple way is simply to replace x with minus x. And then we get 1 over 1 plus x equals 1 minus x plus x squared minus x cubed plus, and so on, in alternating plus and minus terms. Now, this gives rise to an interesting kind of conundrum, because if you set x equal to 1 in this series, then you get 1/2 equals 1 minus 1 plus 1 minus 1 plus 1 minus 1, and so on. And this was an early kind of conundrum that puzzled the 18th century mathematicians, how to deal with this kind of expression. Because they realized that you could also rearrange this quite easily. You could think of this also as 1 minus 1 plus 1 minus 1 plus 1 minus 1. And when you did it that way, you obviously got 0. But if you rearranged it a slightly different way, if you said, well, this is 1 minus, and then we'll group these two terms together, 1 minus 1, and then minus 1 minus 1, minus 1 minus 1, and so on, then all these 1 minus 1s are 0, and then we get 1. So clearly something is a little bit fishy here if 1/2 is equal to 0 is equal to 1. And so there was definitely a conundrum, and people debated what is the right way of thinking about infinite series like this. I'm not sure if it was entirely resolved, but I think one thing that sort of became clear as time went by is that there's a sort of a big difference between working with polynomials and x's and working with a series of numbers. Okay, so basically algebra with infinite polynomials, or power series, is often safer than calculations with infinite series of numbers. Safer than infinite series of numbers. Well, I mentioned just a few things that we've already touched upon, but if we take this 1 over 1 plus x series and we integrate it, then we get log of 1 plus x equals x minus x squared over 2 plus x cubed over 3 minus x to the 4th over 4, and so on. So that's obtained from, let's call this star, from star by integrating. And another important series that was one of Newton's favorite was the binomial series for a general exponent p. 1 plus p times x plus p times p minus 1 over 2 times x squared plus p times p minus 1 times p minus 2 all over 1 times 2 times 3. Maybe we could write that as 1 times 2. X cubed, and so on. So this is finite. This is a finite sum if p is a positive integer like 5, because of these terms here. If p is 5, then eventually they all become 0. But otherwise, it's infinite. Now, there's an important formula that I want to talk about because it's rarely mentioned in calculus books these days, although it's both historically very important and it's also, I think, quite of independent interest. So this is a formula that ought to be in calculus text, but often isn't. It's the Gregory-Newton interpolation formula. And it arises when we have a function which is known at a regular sequence of points, whose values we know at a regular sequence of points. So for example, suppose we have a point A, and then over somewhere A plus B, and then over a little bit further A plus 2B, A plus 3B, and so on. So we have a separation of B between all these adjacent points. And the question is, if we know a function f at all these equally spaced points, can we recover the function's values at intermediate points? That's the question. If f of x is known for all these points, x equals a plus nb, where n is 0, 1, 2, and so on, then what is f of some random point? Is there any way of figuring out or interpolating using the information from these discrete points to figuring out what the function should be in between? And it turns out that for many functions at least, the answer is yes. In particular for polynomials and for power series functions, the answer is yes, and the formula is a very interesting one. Okay, what is it? Well, to introduce that, I need to talk a little bit about a difference operator. It's natural whenever you have a sequence, you can take differences of successive elements in the sequence, and you get another sequence. And the standard notation for the difference operator is this little triangle operator. So we define delta f at some point, let's say A, to be f of A plus B minus f of A. So the value at B more minus the value at A. So we can do that at not just at A, but we can do it also at A plus B. So that would be f of A plus 2B minus f of A plus B, etc. And then you could take the difference of the difference, usually denoted with a delta squared, f of A. So that's the difference operator f at A plus B minus the difference delta f at A. So if you take this formula and you subtract this one here, then explicitly you're going to have f of A plus 2B minus 2f of A plus B plus f of A. And then you can take the third difference. Well, that would be the difference of the second difference of f of A plus B minus the second difference of f at A. And that turns out to be f of A plus 3B minus 3f of A plus 2B plus 3f of A plus B minus f of A. And so now in terms of this notation, this difference operator notation, here is the interpolation formula of Gregory and Newton. That f of A plus h, where h is now some rather random step, not necessarily a multiple of b. This is f of A plus h over b times the difference del f of A plus h over b times h over b minus 1 all over 2 factorial times del squared f of A plus, and so on, and I'll write the next one, h over b times h over b minus 1 times h over b minus 2 all over 3 factorial times del cubed f of a, and so on. So what is needed here in order to compute is we need to know the function's value at a. In order to calculate this thing, we only need to know its value at a and at a plus b. To know this thing, we need to know its value at a plus b, and a plus 2b, and so on. So all what we need for the entire series is just to know the function's values at these discretely spaced points. And then, if we know that, we can cook up this expression that allows us to calculate, say, a value there. That would be h. So that's f of a plus h. That would be that point there. We would be able to calculate the function's value at that intermediate point. Now, a little bit of thought shows this is not going to work for an arbitrary function. If you just draw some random function, there's no way that the function can tell what the intermediate values are from the values just at these points. But it does work for polynomials. Works for polynomials f of x, and more importantly, it works for power series functions, which are the kinds of functions that Newton and contemporaries were really interested in, and power series functions. Now it has an interesting consequence also, that if you look at that formula and say, what happens if this separation starts becoming very small? If b starts getting close to 0, then these equally spaced points become closer and finer, approaching sort of a uniform grid. And then the formula sort of simplifies into something more familiar involving derivatives. The formula due to Brooke-Taylor, called the Taylor series of the function. So as b approaches 0, we get Taylor's theorem. And Taylor was also a contemporary of Gregory and Newton, but maybe 40 or 50 years afterwards. So what's the idea there? Well, the idea is that, well, I'll write down what Taylor's theorem is. It's that f of a plus h equals f of a plus, I'll write the h on this side, although it's usually more common to write on the other side, h times f prime of a plus h squared over 2 factorial times f double prime at a plus h cubed over 3 factorial f triple prime at a, and so on. And the reason is that when you look at an expression like this, say if you look at this thing here, that coefficient del f of a over b, what was del f of a? It was actually f of a plus b minus f of a. So if we divide that difference by b and let b go to 0, that's exactly the derivative of the function at a. And similarly, the next term, for example, if you look at del squared of f at a divided by b squared, then that goes to the second derivative at a. So for example, in the second thing here, if you take this factor of b out and put it in front under there, then there'll be essentially an h squared left up here. And then this divided by the b squared goes to the second derivative. One of the reasons these days that this interpolation formula is maybe not considered important enough to make it into a lot of calculus texts is that these days we have calculators to compute a lot of standard functions for us. But in the 17th century, people had tables to compute things. And the tables were constructed with a lot of work. So Napier constructed tables of logarithms, for example. So if you wanted to know what the log of 4.3974 was, whatever I said, okay, you wanted to know what that thing is, then you had to look in the logarithm tables, and maybe you could find a value for log of 4.7. You knew what that was, and maybe you knew what log of 4.8 was. But that was as much information as the tables gave you. So you had to either eyeball, well, say we're somewhere in between here, closer to here, right? And you could kind of guess. But they wanted to do better than that, so they wanted to have a more systematic way of how do you go from a table of known values to calculating a value somewhere in between. Very practical, important problem. And so you could see the motivation for the interpolation formula. Interpolation was a big deal back in those days. Okay, so now we come to Leonhard Euler, who was, as I've said repeatedly, the most important and greatest mathematician of the modern era, and second only to Archimedes in terms of the greatest mathematician of all time. He was a remarkable person who was born in Basel in Switzerland and spent a lot of time at the Academy in Berlin. And he also bounced back and forth to St. Petersburg in Russia, where he ended up spending most of his career. And he had a long and prolific career. He also had lots of children. He was very pious, religious, sort of plain-spoken person. And he produced huge amounts of first-rate mathematics. So he produced more mathematics than anybody else in history, much more than anybody else, really. His collected volumes, would extend beyond the reach of my arms. During his time in Berlin and St. Petersburg, there were academies where all the mathematicians were supported by an academy. Perhaps more than universities, it was these academies that sponsored academic research. And the academies would have a journal that would report and allow members to publish. And during his years there, he would often be responsible for 50% of all the publications of the entire academy in that year. Almost every week there would be a new paper by Euler. But they weren't just going over the same old thing, right? They were wide-ranging over all areas of mathematics. Everywhere he was interested, he had made contributions in every direction. So he's, in some sense, he's the father of graph theory. In some sense, he's the father of topology. He's probably the father of analytic number theory. He's a key figure in differential equations and the calculus of variations. He made important contributions to astronomy, to mechanics, to physics, to elastic bodies. Number theory, very important contributions to number theory. The list goes on and on. He pretty well did everything. And he also wrote very important textbooks. One of his textbooks, which is called the Introductio in Analysis Infinitorium, something like that. Introductio in Analysis Infinitorium, published in 1748. It's really the world's first calculus textbook. And some people have said it's also the world's best calculus textbook still. That I've heard people argue that students at universities in 2011 would be much better off if they ditched their first year calculus books and all studied from Euler's work 250 years ago. There's probably something to be said about that. So almost so many things so standard topics that you learn about were first treated by Euler and laid out very clearly by Euler in works like this. So let me just very selectively choose a very few things. Okay, one could talk for weeks about what Euler did, but I'll just mention a few small things to give you a sense of some of the things that he was doing involved with infinite series. So the first kind of series that people tried to calculate, which they couldn't, was this one. 1 over 1 squared plus 1 over 2 squared plus 1 over 3 squared plus 1 over 4 squared, and so on. The sum of the reciprocals of all the squares. Now people knew for a long time that the harmonic series, 1 plus 1/2 plus 1/3 plus 1/4 plus 1/5 plus 1/6 plus 1/7 plus 1/8, etc., okay, that actually diverges. That goes back to Oresme in the 1300s, maybe 1350. Oresme realized that this series diverged, which means that if you keep adding those terms, even though you're adding less and less all the time, the total grows slowly and slowly and slowly beyond any bounds. Never stops, just keeps on growing bigger and bigger and bigger. And the way Oresme realized this was to say, look, here's the argument. We're just going to think in terms of grouping these terms in powers of 2. So we'll group this one together, and then we'll group these two together. And then we'll group the next 4 together, and then the next 8, and so on. And by doing that, he could observe that this group of 2 here, 1/3 plus 1/4, that's bigger than 1/4 plus 1/4. Okay, that's bigger than or equal to 1/4 plus 1/4, which is 1/2. And this next group of 4 terms is bigger than what you get when you replace each of one by the smallest. 1/8 plus 1/8 plus 1/8 plus 1/8. And 4 times 1/8 is also 1/2. And then if you take the next 8 terms and you add them up, you compare them all to the last term, which is 1/16, you get another group which is bigger than 1/2. So you can keep taking a segment of the series which is bigger than 1/2, and you can keep doing that as far as you want. So it's 1/2 plus 1/2 plus 1/2. It goes up beyond any limit. So we say it diverges. But it was pretty obvious that this thing didn't diverge, that it actually zeroed in on some number. If you keep adding these things together, it doesn't keep getting bigger and bigger and bigger. It starts approaching something because the numbers that you're adding are in some sense smaller than the numbers over there because you're squaring them. The Bernoullis made lots of calculations with various series, and they knew how to calculate various series, but it was Euler who first established this thing, and sort of remarkable thing. It's pi squared over 6. Which made people stand up and pay attention because pi, what's pi doing in there? Pi squared over 6. Well, we've seen that pi, we have expressions for pi in terms of 1 and 1 minus 1/3 and so on. So it's maybe not that surprising, but it was still a fabulous formula. And it's interesting to see how Euler got it. Okay. He derived some interesting things along the way. So he used Descartes' factor theorem. This was a result, very important result of Descartes, which people learn in high school, which is that if P is a polynomial and P of, say, some value R equals 0, then X minus R is a factor of P of x. So zeros of polynomials correspond to factors of that polynomial. So back in those days, these mathematicians all knew about each other's work largely. You know, Euler would have known all of Descartes' work and Newton's work. He would have studied their works. There weren't that as many mathematicians as there are now. And so it was a little bit easier to keep track of things. And they would write letters to each other. There would be a lot of correspondence. Euler corresponded a lot with the Bernoullis and with other people. So what's the proof of this, of Descartes' thing? Well, suppose that the polynomial, let's write it as P of x equals a0 plus a1x plus a2x squared. Let's go up to an x to the n. And let's just substitute another value, say y, right below it. a0 plus a1y plus a2y squared, and so on. A and y to the n. So if you take the difference between these things, you get P of x minus P of y equals, well, these cancel, and you'll get a1 times x minus y plus a2 times x squared minus y squared, and so on up to a sub n times x to the n minus y to the n. But each one of these terms is divisible by x minus y. And we all know that x squared minus y squared is x minus y times x plus y. But that's also true for these higher things. So if you take something like x to the n minus y to the n, you can write it as x minus y times x to the n minus 1 plus x to the n minus 2 times y plus x to the n minus 3 times y squared, so decreasing powers of x, increasing powers of y, all the way up to eventually just y to the n minus 1. That's like, for example, x cubed minus y cubed is x minus y times x squared plus xy plus y squared. And since that works for all of those factors, we can write this as x minus y times some polynomial q of x. Because we can take that factor of x minus y out from all of the terms on the right-hand side. So that's a general relation. And now suppose, let y be r, where r is our zero of the polynomial, where p of r equals 0. What are you going to get? Well, on the left-hand side, you're going to get p of x minus p of r, but p of r is 0, so you'll just have p of x. And then on the right-hand side, you'll have x minus r times q of x. So if r is a 0, in other words, if p of r here is 0, then p of x is x minus r times some polynomial. So that's a proof of Descartes' factor theorem. Okay, so how did Euler use Descartes' factor theorem to derive this remarkable identity with the sums of the reciprocals of the squares? Well, what he did is he applied it in a rather ingenious, maybe somewhat courageous way. He applied it to something that you might not think about applying the factor theorem to, something which is not exactly a polynomial, namely to the function sine x. Okay. Euler knew that it was pleasant to think about sine x as a function, and that you could graph it in the usual way. Okay, and it goes from the values 1 to minus 1, and it has a 0 at 0, and it has a 0 at pi, and at 2 pi, and at 3 pi, and also at minus pi, and at minus 2 pi, and so on. So sine x has zeros at, well, at x equals 0, at plus or minus pi, and plus or minus 2 pi, and so on. So Euler said, okay, why don't we think about that as a polynomial? I know it's not a polynomial, but let's imagine it's a polynomial. What kind of polynomial has zeros at x equals 0, plus or minus pi, plus or minus 2 pi, etc.? Well, you have to think a little bit about whether those zeros are single zeros or double zeros or triple zeros. But you can kind of tell the way the graph goes through each of these that these are just single zeros. They're not zeros of this kind, like y equals x squared kind of zeros. Meaning that each one of these corresponding factors should really appear exactly once in the factorization of sine of x. Now, most students will not have seen the factorization of sine of x, but Euler wrote it down. So what is the factorization of sine x? Well, here it is. Sine x is, well, it has x as a factor because it has a 0 at x. But it also has factors at plus or minus pi. And for each one of those, there's a factor like this. This is actually combining the factor at pi and at minus pi. Okay, it's a little bit, it doesn't look quite like a usual factor, but instead of writing pi minus x, so instead of writing pi minus x times pi plus x, I'm taking this thing here and dividing both of them by pi squared. We could always normalize. So if we divide by pi squared, then that means that coefficient is 1. That's kind of good. And then there's a corresponding term for the next pair, the 2 pi and the minus 2 pi. 1 minus x squared over 2 squared pi squared. And then 1 for the next pair, 1 minus x squared over 3 squared pi squared, and so on. So this is an infinite product, not an infinite sum. It's like a polynomial with a lot of factors, infinite number of factors. Now Euler had to know something to do this. Well, he had to know quite a few things, but he had to know. Yeah, you need to know that if you look at sine x over x, that ratio goes to 1 as x goes to 0. So if we divided this by x and let x go to 0, then each of these terms would come close to 0, and then the whole thing would go to 1, which is telling us that there's no constant here. There's no constant like phi or pi or anything else out front. The constant is actually 1 as a result of that. Okay, so now what did Euler say? All right, now Euler said, well, let's just expand this thing out. So expand. How do you expand it out? Well, it's just like a polynomial. The lowest power is x. You get x by multiplying 1 times 1 times 1 times 1, keeping on going. So that's the first term, x. What's the next smallest power of x? Well, it'll always be this x. So the next thing you can multiply it by is an x squared. So there'll be a minus x cubed. And what's the coefficient of minus x cubed? How do you get an x cubed? Well, you get it by taking this times this and all the other ones, or this times this and all the other ones, or this times this and all the other ones, and so on. So the coefficient is, here it will be 1 over pi squared, and here 1 over 2 squared pi squared, and over here 1 over 3 squared pi squared, and so on. And then there's additional terms. The next one will be x to the 5th times something. You can try to figure out what that term might look like. But Euler knew also, as did Newton, that sine had also the expression x minus x cubed over 3 factorial plus x to the 5th over 5 factorial. So that goes back to Newton, or indeed to the ancient Indians. Okay, but now we're in a position of comparing. Now we can compare this term with this term here. They've got to be equal. So you compare coefficients of x cubed. And what do you get? Well, you get that 1 over pi squared times 1 plus 1 over 2 squared plus 1 over 3 squared plus and so on equals 1 over 3 factorial. And so if we multiply by pi squared, we get the sum of this series is pi squared over 6. He also established that 1 over 1 to the 4th plus 1 over 2 to the 4th plus 1 over 3 to the 4th plus 1 over 4 to the 4th and so on, that had a similar expression. In fact, maybe you can try to derive that from this by looking at the next terms. That's equal to pi to the 4th over 90. So try it. In fact, he got a formula for all the even powers. So in general, 1 over 1 to the 2n plus 1 over 2 to the 2n plus 1 over 3 to the 2n plus and so on. He got this formula. That's minus 1 to the n minus 1 times 2 pi to the 2n over 2 times 2n factorial times b sub 2n. Okay, what is b sub 2n? It's a Bernoulli number. B sub 2n is a Bernoulli number. Okay, these were introduced by James Bernoulli in some work on probability. And I'll tell you what some of the values are. So b sub 2 is 1/6. B sub 4 equals minus 1/30th. B sub 6 equals 1/42nd. B sub 8 equals minus 1/30th. B sub 10 equals 5/66, and so on. And probably the easiest way of defining what they are is through this power series. That if you take x over e to the x minus 1, what is that? Well, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial and so on. So if you subtract 1, you just remove that and there's an x on top. So if we divide sort of by x, this is the same as 1 over 1 plus x over 2 factorial plus x squared over 3 factorial plus and so on. So if you take the inverse or the reciprocal of that infinite series, then you will get the sum n equals 0 to infinity, b sub n x to the n over n factorial. That's the definition of one definition of the Bernoulli numbers. Again, this is something you can do by hand. You could just take the reciprocal of this or try to find the reciprocal of this by letting it be as some arbitrary sequence and multiplying this by that arbitrary series and equating coefficients term by term. Bernoulli also gave a recursive definition for the Bernoulli numbers in terms of previous Bernoulli numbers, but we won't write that down. So one thing that's kind of interesting here that maybe we should remark on is that this formula for the sum of the power, the sum of the reciprocals of the powers, well, we have one for the sum of the reciprocals of the squares. We have one for the sum of the reciprocals of the fourth powers and also of the sixth powers and the eighth powers and so on. But we don't have any formula for the sum of the reciprocals of the third powers, or the fifth powers, or the seventh powers. In fact, no one knows a formula for those ones. It's a famous unsolved problem. No one knows a formula for the sum of the reciprocals of the cubes. In fact, only in 1981, I think, did a French engineer, I think it was, I don't think he was a professional mathematician, named Apéry, discover a nice elementary proof of the fact that case 3 is actually not a rational number. So to talk a little bit more sensibly about that, Euler talked about the zeta function. So we can introduce a function. We can define zeta of s, say, to be 1 plus 1 over 2 to the s plus 1 over 3 to the s plus 1 over 4 to the s, and so on. So what do we know about this? Well, we know that when you let s equal 1, then you get infinity because the harmonic series blows up. That's our Resbay's result. Okay, that means it has a pole. And we know that zeta of 2 is pi squared over 6. And we know that zeta of 4 is pi squared over 90, pi to the fourth over 90. And it was only in 1981 that Apéry proved that zeta of 3, whatever it is not a rational number. I remember when that happened. That was quite a remarkable thing because no one thought that you could kind of get at that through elementary means. So we don't know what the story is for the other odd values, and we don't really have an expression for a zeta of 3. This is sort of typical what happens if you write down some random series. These aren't random series, but if you write down a random series and ask, well, what's the sum? It's almost never the case that you can be able to say what the sum is except to say that it's just itself. It's just the way it is. So I can't leave the zeta function without mentioning a very important factorization that Euler discovered for the zeta function, which turned out to have very big ramifications for mathematics in the 19th and 20th century. This is this formula here that you can write it as an infinite product. Euler liked infinite products, just like sums. And here's the product. 1 over 1 minus 1 over 2 to the s times 1 over 1 minus 1 over 3 to the s times 1 over 1 minus 1 over 5 to the s times 1 over 1 minus 1 over 7 to the s. What do you think the next term is? 11, yes. 1 minus 1 over 11 to the s. So it's a product over all the prime numbers. Okay, all the prime numbers here. And, well, each one of these is like an infinite geometric series. So this first one here is really the infinite geometric series 1 plus 1 over 2 to the s plus 1 over 4 to the s plus 1 over 8 to the s, and so on. And then the next one is all powers of 3. 1 plus 1 over 3 to the s, plus 1 over 9 to the s, and so on. The next one's all powers of 5. 1 plus 1 over 5 to the s, plus 1 over 25 to the s, and so on. And once you write it this way, it's almost becoming clear why it's true. Okay? The reason it's true is because of the unique factorization of numbers. We know that every number factors into primes in exactly one way. So for example, if you look at 12, okay, 12 is 2 times 3. So if you look at the term 1 over 12 to the s, just look at where does that come from? Well, that comes in this product by taking the term 1 over 4 to the s and multiplying it by 1 to the 3, 1 over 3 to the s, and using the 1s for all the other factors. And since you can kind of do that for every natural number, you can factor it, and then you can sort of see which, how many powers of 2 do you need, how many powers of 3 do you need, how many powers of 5 do you need, and so on, to express that number. That will correspond to the factorization. This function of s, zeta of s, it blows up at s equals 1. What does it look like? So there's s equals 1. It blows up. At s equals 2, here's s. At s equals 2, we know it's pi squared over 6, which is, a little bit somewhere between 1 and 2. And then at 3, it's something will be, so it goes down like this, some way. It blows up. It doesn't look that interesting, but it turns out that you can extend this zeta function to complex values. Once you know about complex numbers, you can define what this zeta function means for s being a complex number. Okay, so if you have the complex plane with 1 here and I here, then this function, which we've just been talking about so far, having values on the positive real line, can be extended into the whole complex plane. And then it turns out that, okay, it's got some zeros here somewhere, but there's this line, the line where the real part is a half. Okay, and it turns out that Riemann, great German mathematician of the middle of the 19th century, conjectured that this extended zeta function, once you'd extended it to the complex numbers, that all of its non-trivial zeros lie on this line, real part equals 1/2. And that's the most famous problem in mathematics today. That's the most famous problem. It's called the Riemann hypothesis. And you might say, well, why should that be famous? Well, it's because it tells a lot about prime numbers. So all kinds of deep properties of the prime numbers are encoded in this analytic information about where the zeros of this zeta function are. And the fact that it has something to do with prime numbers is already obvious from Euler's product expansion. Okay, but it does take some significant analysis, complex analysis too, and some number theory to appreciate the Riemann hypothesis, its full glory. But there's a lot of evidence for it. So Euler established a lot of the foundational work on sort of high school and undergraduate mathematics that we deal with today. And in particular, he understood the exponential and logarithm functions very well, and they were very important to him. And he also investigated those functions in the complex plane. So in the 18th century, people started working with complex numbers a little bit more confidently than they did in the 17th century. And Euler was quite adept with complex numbers, as we'll see. So I remind you that if x equals log y, then y is the inverse function, which we call e to the x. And Perhaps the best way of introducing these functions is to start with log y. So log of y is defined to be the integral from 1 to y of 1 over t dt. This is a definition of log. And then it's not too hard to see that the derivative of the log function, because it's an integral, so its derivative is just what's inside here, so it's just 1 over y. So in other words, dx dy equals 1 over y. Then if we invert that, then it means that dy dx equals y. Just flip it over. And y being e to the x, it means that this function y has the property that its derivative is equal to itself. So the inverse function of the log function has the very special property that its derivative is equal to itself. And from the power series point of view, it means that you can write it down as a power series, and you can sort of figure out what it is step by step, because it's got to be equal to its derivative. We also know its value at 0 is 1, so if it starts with 1, then the next term has to be x, because the derivative of this has to be that. And then the next term has to be x squared over 2, because the derivative of this has to be that. And then the next term has to be x cubed over 3 factorial, because the derivative of this has got to be that. So you get the power series for the exponential function. By the way, Euler liked to write it as 1 plus x squared over 1 times 2 plus x cubed over 1 times 2 times 3, and so on. Euler liked to be very explicit about things. He wrote things out fully, and he was not afraid of making calculations and having a long formula. In terms of pictures, if we have x and y, if we start with the function 1 over x, and there's 1, and we integrate it to get the log function, then we get log of x. So this is just the area underneath the 1 over x function. And if we look at the various values, 1, 2, 3, 4, 5, and so on, then the area underneath that curve can be approximated with a bunch of rectangles. The first rectangle will have height 1, and then the next rectangle will have height 1/2, because that's a half, and then the next rectangle will have height 1/3, and so on. And so in some sense, there's an approximate sense in which the log function should be a lot like the first few terms of the harmonic series, so that 1 plus 1/2 plus 1/3 plus all the way up to, say, 1 over n should be pretty close to log n. The integral is approximated by all those areas of rectangles. In fact, Euler realized that the difference between those two things approached a certain number. The limit as n approaches infinity of 1 plus 1/2 plus 1/3 plus all the way up to 1 over n. If you subtract log of n, you get some number, usually called gamma these days, has the value, approximate value, 0.5777218 dot dot dot. And that's known as Euler's constant. Euler also used the exponential function with complex values, and he came up with the famous formula e to the I theta equals cos theta plus I sine theta. Familiar to all students of complex numbers, complex analysis. I want to read a little bit from this Introductio in Analysis Infinitorium. The section on circular functions. So the circular functions, cosine, sine, tan, and so on, they're quite a source of logical problems in undergraduate mathematics because it's rare that you actually pin them down very precisely. Most treatments of calculus sort of suppose that these functions have already been defined back in high school, and that's not necessary to be very clear about what these functions actually are and what the various proofs of the various claims made about them are. So it's even today a source of logical problems in mathematics. But anyway, here's Euler talking about, in his rather introductory text about how we should go about thinking about these functions. So after logarithms and exponential quantities, we shall investigate circular arcs and their sines and cosines, not only because they constitute another type of transcendental quantity, but also because they can be obtained from these very logarithms and exponentials when imaginary quantities are involved. Let us therefore take the radius of the circle to be 1. Then it is obvious that the circumference of this circle cannot be expressed in rational numbers, but it has been found that the semicircumference is, by approximation, pi equals 3.141592653589793, and Euler then goes on for 127 decimal places. So there's someone who's serious about calculus. Okay? It doesn't say that it's just roughly 3.1414. It's 127 decimal places. He gives it to you. Okay. For which number I would write for short pi. So that pi is the semicircumference of the circle of which the radius is 1. Or pi is the length of the arc of 180 degrees. Now, if we denote by z an arbitrary arc of this circle, then we shall usually consider of this arc mainly the sine and cosine. I shall denote the sine of the arc in the future in this way by sine of z. Maybe that's z there. Sine of z, and the cosine by cosine z. And he mentions that sine of 0 is 0, cosine of 0 is 1, and sine of a half of pi over 2 is 1, and cosine of pi over 2 equals 0. And then he derives a whole host of other trigonometric formulas and identities which are well known. Then he says that since sine of z squared plus cosine of z squared equals 1, we shall have by factorization this formula, cosine z plus I sine z times cosine z minus I sine z equals 1. Here he's kind of making reference to what we would now say as, well, we have a complex number on the unit circle. Maybe W equals cos theta plus I sine theta. This is the statement that the complex number W times its conjugate is 1, which is equivalent to saying that its mod squared is 1. And then he mentions De Moivre's theorem, which is cosine n theta plus I sine n theta equals cosine theta plus I sine theta to the n. And from this he gets cosine of nz, okay, he's using z, cosine nz equals cosine z plus I sine z n plus cosine z minus I sine n z to the n over 2, over 2, plus a similar formula for sine z, sine nz. Then he says, well, now what we can do is we can expand these things out in terms of the binomial theorem. Because we have something plus something else to the nth power, we can expand that out. So when we develop these polynomials in a series, we shall get cosine nz equals cosine z to the n minus n times n minus 1 over 1 times 2 times cosine z to the n minus 2 times sine z squared plus etc. And similarly a formula for sine nz. Now he says, now let the arc z be infinitely small. So let z be very close to 0. Then we get that sine of z is equal to z. So if z is very small, sine of z and z are almost the same. And cosine z equals 1. Now let n be an infinitely large number. Okay? Now let n be almost infinitely large. So this is going to get infinitely small. This is going to get infinitely large. But their product should be something that we understand. But such that n times z equals a finite value v. Okay, so this is the kind of argument that these days we might be a little bit skeptical about, or we would maybe want to say it in some more precise way. But typically whatever Euler said, there was some more precise way of saying it, but this is the language he used. Okay, so what happens to a formula like this? Well, then this kind of simplifies. Then we get that cosine v equals, so cosine z we're saying is 1, okay, that's 1, and then minus n times n minus 1 over 1 times 2 times cosine z to the n minus 2, and he ends up getting v squared over 1 times 2 plus v to the 4th over 1 times 2 times 3 times 4, and so on. In other words, he gets the usual power series for the cosine function from this using some kind of limiting arguments. And I'll just give you a few more formulas that he writes in this chapter. So including the formula as he writes, 1 plus z over epsilon to the z epsilon equals e to the z. So this where epsilon is, okay, it's 1 over n as n goes to infinity. Oh, no, maybe I should say, no. Where epsilon is infinity, we would write e to the z equals limit as n approaches infinity of 1 plus z over n to the n. And then he writes down the famous formulas. Cosine v equals e to the iv minus e to, plus e to the minus iv over 2. And same sign of v equals e to the iv minus e to the minus iv over 2I. Well, this only touches on a very small part of all of Euler's work, but it's quite clear that a lot of the ways we think about the exponential functions, the log functions, the circular functions were well known to Euler, and basically we follow his treatment in a lot of different ways. But one big difference is that these days when we talk about series, power series in the calculus course, the emphasis is generally on convergence of series, whether a certain series converges or not. To Euler and his contemporaries, that was not really that interesting, because you could kind of think of a series as being some kind of infinite polynomial independent of whether it converged or not. So it turned out in the 20th century that that point of view kind of came back, and there's now a branch of mathematics called formal power series, which justifies, to a certain extent, a lot of the manipulations that Euler and his contemporaries made. And it may be, I think, that the future will still see perhaps a return to the more algebraic orientation to series and analysis that Euler and after him Lagrange sort of pioneered. So next time we're going to talk about arguably the greatest development in modern science, not just mathematics, but which is the mechanics initiated by Isaac Newton. So really the start of physics in the 17th century. So we're going to talk about mechanics and really the resolution of probably the greatest problem in the scientific history, namely what's happening with the planets. They figured that out in the 17th century, and so we'll talk about that. So I'll see you then.